The next session, and our next speaker is Paul Goldberg. He's going to talk about the complexity of the homotopy method.
Okay, thank you, Noam. Can everyone hear me? So what I will be telling you, the main result that I will be telling you about today is the fact that it is not merely p-pad complete, but in fact p-space complete to find the equilibria that are found by the computed by the Lemke-Howson algorithm. So what we shall see then is that our old friend the Lemke-Howson algorithm can in fact, with a bit of effort, be made to serve as a proxy for generic polynomial space-bounded computation. And that's a bit of a paradox, in fact, if you think about it, because the Lemke-Howson algorithm was designed for a very specific purpose, of course, and furthermore it is efficient in practice. And we could contrast that with other exponential time approaches which are inefficient in practice, such as support enumeration for solving two-player games. And what we see there is that support enumeration, for example, is not only inefficient in practice, but it's pretty straightforward to see that it requires exponentially many steps to find a solution. In contrast, the sort of most relevant previous paper to this result is the one of Savani and his then supervisor Bernard von Stengel, who showed that it's in 2004 that it takes exponentially many steps for Lemke-Howson in the worst case. So, you know, part of the future work perhaps is coming to terms with this paradox, trying to explain why it is that Lemke-Howson is, in a sort of strong sense, finding something that is computationally much harder to find than other algorithms. So here is a quick overview of the talk. I will tell you what I mean by homotopy methods and how the Lemke-Howson algorithm is in fact a homotopy method, and some of the proof ideas. It turns out we can make some nice pictures to illustrate what's going on. And finally, I suggest some open problems, you know, some further work, which you can tell me whether you think they're the right questions to ask afterwards. So, what's a homotopy method then? It's a very simple principle. So, suppose we have a game that we want to solve. Here's a n by n two-player game written in a fairly standard diagrammatic form for n equals 3, of course, and we say, okay, here's this game, you want to find a Nash equilibrium of it. And so, what does the homotopy method envisage doing? So, right, here is a copy of the game of interest, the one that we really want to solve. And what I do to solve this game is that I start by making a version of it in which I've just modified the payoffs, not the structure of the game, just the payoffs, in such a way that there is a really easy, obvious, easy to find Nash equilibrium, so that I might, for example, do that by paying each player 1 point to use his first strategy and 0 to use any of the others, so it is obvious what they should be doing there. And what I continue by doing then is that I will sort of continuously tweak all the payoffs to get from here to here, so that if I just sort of parameterize this process by a parameter t, there's t equals 0, t equals 1, and at t equals 1/2, the process that is being suggested by these numbers is that we just sort of take a weighted average of the payoffs in the game, and we sort of keep track of the equilibria as we proceed with this process, and we hope that we end up with an equilibrium of the game that we really want to solve, the one over here. Okay, so it's you know, the basic idea, I think, is quite simple and straightforward, but of course you will find that implementing it is not quite so simple and straightforward. So a bit of notation there. I use a kind of continuum of games, GT, where G, so T is the, you know, the parameter of this continuum of games. T equals 0 is the easy game. T equals 1 is the interesting game. So why does it work? So there is this, this result that is not to be confused with Brouwer's fixed point theorem. And Browder's fixed point theorem says something a little bit more complicated. So what does it say then? I'll just you know, go through it quickly and then tell you how we apply it to the purpose of solving games. So if we have a continuum of continuous functions, which I sort of use a similar notation to games, so f sub t, where t is going to go from 0 to 1, represents each ft then is a continuous function from a compact domain to itself, and so each of these ft's then will have at least one Brouwer fixed point. Then it turns out that we can say, I mean, I've not told you exactly what I mean by a continuum of continuous functions, but you can sort of imagine what I mean, right? It means that as these, you know, as ft and ft prime, as t and t prime get closer and closer together, then these two functions, ft and ft prime, should start to look like each other, right? So we find that there's a kind of topological one-dimensional path of fixed points that connects a fixed point of f0 with a fixed point of f1. So that there's this kind of path that we can follow. In the context of games, these functions that we're looking at would be, you know, given a game, we associate with it a function that sort of tells the players in which direction they want to move. So the domain then, this domain D, is the domain of mixed strategies for the players, mixed strategy profilers for the players, I should say. And the function associated with a game would be a sort of function that says, you know, given a mixed strategy profile, the players want to move in some direction, typically. Unless, of course, they're at a Nash Equilibrium, a fixed point of that function, in which case they are not being, you know, dragged in any particular direction. They're sort of allowed to stay put. So we can represent this kind of situation diagrammatically. So if these sort of ovals then are supposed to represent the domain on which these functions exist, and the red lines and spots are meant to represent fixed points of the function, so that at t equals 1 we might have f1 having 3 fixed points here, here and here. At t equals 0 there is just one fixed point, which means that we know exactly where we should start this to follow this path. And so this Brouwer path then, of course, is this path in red. You know, it starts here at a fixed point here, ends up at a fixed point of f1. And you can see you know, an obvious problem with this approach, which is this section here, which sort of points out the fact that the path is not monotonic in T. We have to backtrack in T as we follow this path, but you know, in principle it can be done. So this is the game. This function corresponds with the game G0. There is one Nash Equilibrium, one fixed point. The game G1, on the other hand, may have a bunch of them. You know, I've drawn an example with 3 fixed points, and you know, this kind of approach to solving equilibria, of course, it's quite nice because it gives you another bit of intuition about why there's an odd number of Nash equilibria. If you sort of buy this idea that the fixed points of functions, they lie on sort of topologically one-dimensional paths, then if you think about how they could possibly you know, connect up with each other, then it sort of makes sense that equilibria of a typical game can be paired off with each other in some sense. So, okay, so as I've mentioned then, the continuous functions in question are just what I'm calling these incentive direction functions. And, you know, I think it's fair to say that the homotopy approach is a natural idea. We can think of it as a kind of criterion for equilibrium selection. So what I'm kind of moving towards here is the idea that the game G0 could be sort of regarded as a prior belief on what the player's payoffs are, and there is some kind of meaningful sense in which we are finding an equilibrium that might be regarded as being better than other ones, but I do not want to push that idea too far. Let me state a problem linear tracing then, which says...
you can quote Hassan on that.
Sorry?
You can and should quote Hassan on that, because that's exactly what he says. And that's his,
yes, I should quote him. You're quite right, I should indeed quote him.
that's exactly
his comment. Yes, yes, thank you. Yes. Yours as well. Great. Okay. Yeah, linear tracing then. It is the problem, computational problem, of finding the equilibrium that is identified by this procedure. And other homotopies, there are other homotopy methods, and in particular then, let's take a look at the Lemke-Howson algorithm, regarded as a homotopy method. And the difference now is that the game G0 is constructed in a slightly different way from the game G equals G1. So here, okay, G is the game that we like to solve. G0 is going to be constructed by giving some player a large bonus to play one specific strategy. And B is chosen to be so large that the player will definitely play that strategy. And the other player, therefore, will make a best response to that particular strategy. So once again, we have an easy-to-solve game because we have incentivized the players to do something, obvious. And what we do next, as you might expect, is that we continuously reduce B down towards 0, except that as I mentioned, typically B does not go down monotonically. We have to zigzag perhaps on the way down towards 0, but we get there in the end, as promised by the algorithm. And the path that we end up following, then, this Browder path, it turns out to be piecewise linear, and the pieces turn out to be connected to each other via the applications of the pivot operations that the Lemke-Howson algorithm performs. Okay, so the Lemke-Howson then is in fact a homotopy approach. So now where does this p-space completeness come from then? It comes from two related problems then. So end of line, so the p-pad completeness of finding an unrestricted Nash equilibrium, it envisages making a reduction from the problem end of line to the problem Nash of solving a two-player game. And it says that we start out with a sort of a large graph and represented by two circuits. So it's an exponentially large graph represented by two circuits that allow you to perform local navigation on this graph, looking for endpoints. It's a graph which has got degree 2, and actually maybe I will skip to my diagrams, which are a little bit nicer to look at. The graph looks something like this then. It is, it's exponentially, it's degree 2, exponentially large, and we are given for free a particular point, which is a source of the graph, and we are told to find some other point that's either a source or a sink, and we know, of course, that there should exist at least one of these solutions, simply because certainly there ought to exist a point at the other end of the line that is begun at this line here. Okay. Now, the p-pad complete problem then, end of line, it says any of these three things is a solution. I've labelled them with gold stars. These are the points where there are these are nodes of degree 1. Okay, and keep in mind though that this graph is it's exponentially large. It's compactly represented using circuits, so that is why it's not just easy to go searching around in the graph for these kind of points. Okay. But these are the solutions in this little diagrammatic instance. Now the problem, which I call it something like other end of this line, find the point that lies at the end of the line that is kind of identified by this starting point that we were given for free. Okay, which is to say this unique point here. Okay, the one that's at the end of the red line that I've indicated on my diagram. This is p-space complete to find, in fact. And the sort of very, very quick overview of why it's p-space complete to find is that these two circuits, which tell you, given a point whether, what are its neighbours, you can think of these circuits as being able to simulate a reversible Turing machine. And each of these points is a kind of configuration of a space-bounded Turing machine. The circuits tell you what the next configuration would be, or the previous configuration. And it's known to be p-space complete to find the final configuration of one of these machines. And so this thing really is p-space complete to find. And so it's sort of related strongly to the starting point of these this p-pad completeness proof. So as you might hope then, if we instead of thinking about end of the line, this problem here, we just sort of change our minds and ask for this problem, and then we try to sort of make a similar reduction to the problem of Nash equilibrium in games. We sort of hope that we might find some kind of, more difficult Nash equilibrium selection problem. That's a sort of high-level overview of what's going on here. So what I have to do then is to tell you a little bit about this reduction from end of line to the problem of finding Nash equilibria of games. And there is this key intermediate step of the reduction, a sort of intermediate problem, which is the problem of finding a panchromatic point of a discrete Brouwer function. So what's a discrete Brouwer function? In 2 dimensions then, let me just make most of my diagrams 2-dimensional. Think of this grid here as being exponentially large, okay, and the colouring function, the way these colours are assigned to squares, is using some polynomial-sized circuit, which takes as input the coordinates of a square and it outputs one of these 3 colours, okay? And there is going to be a constraint, a boundary constraint on how these grids can be coloured, which says that the bottom line here must be red, this strip here must be green, and this boundary here must be blue, okay? Now these boundary constraints are important because they make sure that we really have a total search problem on our hands, and that there really exist, in this case, trichromatic points, these sort of points here, which are solutions to this particular instance of the problem. And so here is a sort of copy of this particular little problem instance that I'm going to be concentrating on. The problem that we face is one of finding a trichromatic point, and it turns out to be the case, even in 2 dimensions, that these kind of points, they really are p-pad complete to find, even in 2 dimensions, the result of Chen and Deng's quoted at the bottom there. So, and furthermore then, I'm telling a lie at this stage, okay? But the basic idea is the following, which is that once again there is a rather more specific point, namely this one, a rather more specific solution, which is going to turn out to be p-space complete to find. And it is going to be a solution that is somehow identified by a sort of piecewise, by a line in this diagram, which also, I hope gives you an idea of why it is that this is a total search problem. So what this line is doing is we sort of start at the place where red and green meet each other, and we sort of follow the boundary of these 2 regions where they meet each other, and we keep going, and we're allowed to stop when when we hit the colour blue, and by necessity we stop there, and that is a solution to this discrete Brouwer problem. And so this way of finding a solution, it gives you maybe an intuition about why it is that it really is a total search problem. We're guaranteed to find an answer, and it also indicates the importance of these boundary constraints. It shows you why it is that we, the boundary constraints are what are, guaranteeing the totality of this search problem. Because if we were allowed red and green to be adjacent to each other elsewhere on the boundary, then this line could conceivably, shoot out of the picture somewhere else. So we have a p-space complete problem here. In a little bit more detail, maybe this is a bit too much detail to go into, but I'm just giving you a flavour here of the reduction from end of line to this discrete Brouwer problem. What it envisages then is that each vertex in the graph, which may be hard to see down at the bottom of the picture, they have a sort of strip of red and green corresponding with them. The starting vertex is the one at the end, which is connected nicely to the edge of the diagram. And then we can sort of connect these vertices up to each other with red-green strips that kind of, correspond to the edges of the graph. And there's a slight problem here, which is that what do we do when the strips cross over each other? And what we do, in fact, is that we sort of rewire them so that we avoid any unwanted places where the red and green and blue colours all meet each other at a point other than, this kind of point here. This is the kind of solution that we like, okay? This is a vertex that's only got one edge, okay? So there is a panchromatic solution to this discrete Brouwer problem, which corresponds to a solution to the end of line problem. This gadget, in fact, kind of screws us up a little bit because it means that the topology of these red-green strips no longer corresponds to the topology of the graph, and we get around that by moving to 3 dimensions, in which case we make 3 coloured strips that correspond to the vertices, and we wire them up using edges that have little bridges that cross over each other, and we avoid having to make a sort of crossover gadget that sort of interferes with the structure of the graph, so that's fine. Okay then, so we have to continue this journey from end of the line to Nash Equilibria, and the next stage is that we want to get to the problem of finding fixed points of continuous functions. So what we do next is that we associate each colour with the direction of motion of this function. So within each square then, the colour blue indicates that some continuous function is going to move a point a little bit that way. And, you know, red is up, green is to the right, and so on. And we think of the function as moving each point only a short distance. Let's see what I've said here. Right, so we're going to make a continuous function that sort of encodes the discrete Brouwer function. And what we have to do then is to interpolate smoothly at the places where the different colours meet each other to ensure that we really have a continuous function. Now, the thing to notice about this diagram here is that where 2 different colours meet, we can really interpolate smoothly between them. Okay, we can sort of, the arrows can change directions in a nice continuous way, but where 3 colours meet, such as, you know, here or here or here, these correspond to points where we're arbitrarily close to points that are getting dragged in all 3 directions. And it turns out that any way of interpolating smoothly is going to lead to fixed points of the continuous function. So, as I've also mentioned, this type of thing, this type of continuous function, it can be computed using a sort of polynomial size arithmetic circuit that is computes this continuous function and is derived from the circuit that computed the discrete Brouwer function. So, okay, so we have and you'll also notice, of course, that these boundary conditions are also quite helpful in making sure that the continuous function really does map the domain to itself. You know, at the edges of this diagram, the boundary conditions are now actually ensuring that the domain is mapped to itself, and we do not suddenly jump outside the domain, which would be invalid. We do not want to do that. Yes. Right. So, okay, we've gotten to the stage of encoding continuous functions using these things, and I'm going to show you a homotopy problem now, which turns out to be p-space complete. So, here is a kind of very simple discrete Brouwer function, you know, maybe the simplest possible discrete Brouwer function, which, by the way, is going to correspond with the sort of easy-to-solve starting game G0. This, as you might expect, is done by just colouring the entire inside of this diagram blue, so that, you know, it's the simplest possible function of this type. And what we envisage doing is finding a homotopy then, a continuum of continuous functions that begins here and it ends here. Okay? So what would such a thing look like? It would look like this. Right. As this process goes on, what happens is that there was a fixed point here that has now disappeared. There are 3 fixed points, the one marked with the star and the other 2. And presumably then, by Browder's theorem, these fixed points, these intermediate fixed points, must have moved continuously around this diagram. However, the blue region, this blue region here, was blue throughout the process, so it is a sort of no-go area for fixed points. And presumably, therefore, the fixed point, you know, that began here, it must have moved somehow through the red and green region and ended up at the one marked with the star, that is the, you know, this sort of specific fixed point, that is the p-space complete one to find. So one problem with making diagrams like this is that you can also always think of some way to improve them slightly, and so I then, you know, wondered about making the arrows a bit bigger or smaller to show the magnitude as well as the direction of the function. So just here then, the arrows are quite small where the fixed point really exists, and if we repeat this process once again, this is what happens. So you thought I was lying to you when I said this is where the fixed points go, but in fact halfway through, if I go backwards just a little, halfway through we see a bunch of fixed points that start to emerge all the way down this path, and this is the point at which the Brouwer fixed points, they start to shoot down this path, and they end up at the one that we want them to end up at, and you know, we finish up as before, and therefore then, you know, we have a p-space complete homotopy. So, of course, since I'm running low on time, I do not really have time to tell you about how to encode that stuff using games, but it uses gadgets of the same sort that we use to prove that games are PAD complete to solve. And consequently, it turns out that there is a reduction from linear tracing, which maintains, yes, a kind of close sort of topological correspondence between the paths in the end-of-line instance and the sort of path that the Nash Equilibria follow in these homotopys. Lemke-Howson poses a kind of nice, interesting challenge, which is that Lemke-Howson, then, there are really two possible solutions to Lemke-Howson. They depend on which strategy we initially give the large bonus to. So we have to prove that it's p-space complete to solve, to find any of them, not just one of them. It's relatively straightforward to prove that it's p-space complete to find just one, some specific one, but you know, to find any requires a bit more work, which I will gloss over. So, okay then, I think I can just have time to tell you a few, you know, conclusions, suggested further work, which you know is just my thoughts on the topic, and maybe you have better ideas. So, right, yeah. So I've what I've done, you see, is I've taken a specific exponential time algorithm, and I've said, what is the complexity of finding solutions that are computed by this algorithm? You know, it's about, in a sense, it's a kind of question of looking for shortcuts to the solutions that this algorithm actually finds. And the sort of current problem that I'm slightly obsessed with at the moment is, well, sort of in a similar vein then, we could take some other algorithm, so fictitious play. So this is a very simple, straightforward, iterative approach to finding Nash Equilibria of games. Sometimes it converges to a Nash Equilibrium, sometimes it fails to converge, in which case it fails to converge to a Nash Equilibrium. You might ask the question, given a game, can I tell whether it converges, and if so, which Nash Equilibrium it converges to? Same sort of question. I don't even know whether it's decidable. So that's one question you might ask. And I guess you know, coming slightly closer to the type of result that I've just been showing you, you might more naturally perhaps ask about generalizations of it. So what I've done is, yeah, I've shown you a specific type of path-following algorithm. And I've, you know, we've shown that various kinds of path-following algorithms are p-space complete to find their solutions. And you might ask whether is there some kind of more general result that says that all path-following algorithms are have solutions that are p-space complete to find. That is not true, by the way, of any old exponential time algorithm where, for instance, support enumeration, if you start to think about it, it really corresponds to the problem of finding a lexicographically minimum satisfying assignment, and that's got much lower computational complexity. So do not imagine that everything is p-space complete to find, you know, has solutions that are p-space complete to find if you want their solutions type of thing. Okay, so here is a, you know, sort of quick summary of a fictitious play, if any of you want to take a look at that. Sort of, it's an intriguing problem, you know, what is the solution found by fictitious play? I don't know whether it's a, you know, maybe it's a problem of mainly theoretical interest, but I find it quite an interesting one. So I'll just leave that up for you, though, and I think that concludes my talk. Thank you very much.
Maybe you could
Yeah, I think that's possible. It might be harder because the simplex algorithm has a kind of monotonicity to it. You know, there's a kind of, measurement of progress, isn't there? A sort of potential function, right? That we're trying to sort of locally, optimize. So in that sense, I think we're looking at something that is more difficult, but it is. I think it's still possible. I've not thought very hard about it, I have to admit, but it's a good question.